I want to talk today about this new word we're going to be using a lot in geometry. It's congruent. It's very similar to the word equal, but in geometry we need things to be congruent. We also have some things that are equal, and it's very different times when we'll be talking about equal and when we'll be talking about congruent. So I want to make a comparison between the two things. Here's kind of the definition of congruent. It goes two ways. So if two segments have the same length, then they are congruent. I could also say that if two segments are congruent, then they have the same length. So the if part is kind of what I'm starting with. If I start out and I know that two segments have the same length, then I can say they're congruent. If I start and someone tells me, hey, those two segments, they're congruent, then that tells me that they have the same length. So it depends on what you're starting with. If you're starting with measurements that are the same, then you can say they're congruent. If you're starting with congruent, you can say they have the same length. I'm talking about segments here, but this is going to apply to many, many different things. Anytime you have measurements, measurements are equal. Okay, so when I say equal, I have to be talking about measurements. Congruent applies to figures, so figures can be congruent. So segments, angles, triangles, squares, all those are figures. Those are congruent. You would never say a triangle equals another triangle. A triangle is congruent to another triangle. The length of a side of a triangle can equal the length of the side of another triangle, but the sides themselves are congruent. This is what the congruent symbol looks like. So it even looks like equal. It's an equal sign with a little tilde on top, a little squiggly line. So if I talk about my triangle example again. So these two triangles are identical. They're exactly the same. So if this is triangle ABC, and this is triangle DEF, I can say triangle ABC is congruent to triangle DEF. I can't say they're equal, because equal implies they are exactly the same in every way. And the one way that these are not the same is their position. Okay, ABC is over here. DEF is over here. They are not exactly the same because they're not in the same space. They're identical in every other aspect. And that's what congruent means. So every side, so AB is the same length as DE. So I could say the length of AB, which is a measurement, so this represents a number. Okay, because if AB is 5, that's what this represents. This is 5. That's equal to the measurement of DE. But if I wanted to talk about the segments, I would need to say that the segments are congruent. So that's the big difference between equal and congruent. Okay, so that's why we need this word congruent. We need it because when we can't say equal, because equal implies they're exactly the same, so they'd have to be in the same space. When they're not, then we use the word congruent. Okay, the first postulate that we're going to have a lot of postulates this year. A postulate is something that we're told without a definite proof. It's usually something that's so intuitive that it almost doesn't have a proof. When we talked about the definition of a point, that's kind of a postulate. Because points don't have a definition. We just say they're, a dimensionless placeholder. There's no proof of that. It's just so simple, we almost can't explain it because it's so simple. You know, when I say a point, everyone knows what a point is. So when I try to put words to it, it just makes it difficult. So the segment addition postulate is our first one. And this is going to be used a lot when we get to proofs. Because what it does exactly what it says it does. It adds segments together. So it allows us to take two segments and combine them into a bigger segment. So if I've got points A, B, C up here, I can make a segment AB. So there's segment AB. I also have segment BC. The segment addition postulate is going to allow me to say that, well, if I take AB and add it to BC, that's AC. Okay, but in order to do that, the first thing I have to know is I have to know that B is between A and C. And the word between is a phrase that implies that they're collinear. So when you hear the word between in geometry, it means they are on the same line together. So a version of between that does not work. Okay, if I have these 3 points, F, G, H, I could not say G is between F and H. In geometry, I can't say that because in order to be between, G would have to be down on a line that connects F and H. It's not. So G is not between. So I could not say that FG plus GH equals FH. Okay, and we can see that that wouldn't be true, right? Because the length of the red ones added together would be much larger than the length of the blue one. But in my original example, the length of the blue plus the length of the red is definitely going to equal the length of the green. So if I add the length of AB, add the length of BC, that's going to equal the length of AC. That's what the segment addition postulate does for us. So here's another version of it. Okay, if I take the length of AB here and add it to the length of BC, it's going to be longer than what AC would be. Okay, so this is one way. If I start with a picture and I see that I have 3 points and there's one in the middle, I can say the first segment plus the second one equals the third one. This can actually be read the other way. So let's say I don't know if B is collinear with A and C. I don't know, I don't have a picture. Okay, and I want to figure out, is B between A and C? I can go the opposite direction with my segment addition postulate. So I can start with this. If I can show that this is true, okay, if I can show that AB plus BC equals AC, so I'm rewriting it this way. If I can show this, then that's going to mean that this statement is true. So if I can find the length of AB, add it to BC, and have it be the exact same as the length of AC, that's going to tell me that B is in between A and C. In between meaning collinear with A and C. In order to do this, we're going to use our distance formula. Okay, and our distance formula, for those of you who don't remember it from algebra class, is really just a play on the Pythagorean theorem. So let me take a second and just work the distance formula up here. Okay, we use the distance formula when we have points on our coordinate plane. So let's say, for example, I have a point here and a point here, and I want to know how far it is from this point to this point in a straight line. What's the straight line distance between these points? Well, my first point here is at 2, 2. And this point is at 5, 6. Well, the distance formula, if you guys remember it, here's what it looks like. Okay, I take the square root of, I take x2 minus x1 squared plus y2 minus y1 squared. And all that happens underneath the square root. So if I go through using the distance formula, I would have, this is my x2, y2, this is my x1, y1. I'd subtract my x values, so 5 minus 2, that gives me 3 squared. Subtract my y values, I get 4 squared. 3 squared is 9, 4 squared is 16, 9 plus 16 is 25. The square root of 25 is 5. So that means the distance from here to here is 5 units. One note I want to make about this is, let's say I renamed my x1, y1, and x2, y2 so that I went in the other direction. I should still get the same distance. Okay, so if I go through it this way, I'm going to take x2, which is 2, minus x1, which is 5, squared, plus 2 minus 6 squared. 2 minus 5 is negative 3. Okay, but that's still inside the parentheses. Okay, and when I subtract 2 minus 6, I get negative 4, which is still in the parentheses. Now, when you square a negative, you're going to get a positive out. Because this whole thing is being squared. It's negative 3 times negative 3, which is a positive 9, positive 16, and I still get the square root of 25, which is still 5. So that squaring, that kind of takes care of any negatives that we have, because that's going to make sure that we're always getting positive numbers out. If I didn't have one that worked out so nice, we have to use what's called simplest radical form. So I'm just going to change this point so we get one that's not as good. So we'll do this. This should work out pretty nicely. So now this point here is at 610. Okay. So we can use the distance formula again. I want to show you kind of where the distance formula came from. And also this makes a little bit different way of doing it. The distance formula is really just a play on the Pythagorean theorem. Okay, if you don't remember Pythagorean theorem, it's a squared plus b squared equals c squared. And it works in right triangles. So if I make a right triangle using my points. Okay, so I've got this right triangle. This is the symbol for a right angle. And in my right triangle, the two sides that make the right angle are always A and B. And the hypotenuse is always the long side, the side that's across from the right angle. So this is C. So really, if I find this distance, the length of A, which would be 1, 2, 3, 4, and add it to the length of B, which is 1, 2, 3, 4, 5, 6, 7, 8, that should equal C squared. Now look at where I'm getting this 4 and 8 from. In order to get 4, just using my points, I'm just looking at my x change in distance. So if I look at just my x values here, 2 and 6, they are 4 apart. That's the same thing I was doing when I was taking x2 minus x1. I'm finding out how far apart my x's are. So that's where the x2 minus x1 came from in my distance formula. I squared it because I square A. Then I took my change, B is my change in my y value. I take 10 minus 2 to get how tall this right triangle is. So that's why I get the y2 minus y1. And I square it. And this would equal my distance squared, because distance is just the length of c. Well, I don't want distance squared, I want distance. So that's why we're actually square rooting this whole thing to cancel out the squared here. And that's where the distance formula comes from. So if you don't like using the distance formula, you can always make this right triangle and just use the Pythagorean theorem. So if I do 4 squared, I get 16. 8 squared is 64. This equals c squared. 16 and 64 would be 80, which is c squared. So to get the distance, I have to square root, because I don't want to know how long c squared is. I want to know how long c is. So I'm going to square root both sides. So c is the square root of 80. Now, we don't want to leave it as the square root of 80, because there's something called simplest radical form. It's a standardized form for expressing radical expressions, which ensures that if I get an answer and you get an answer, if we make sure that we both put our answers in simplest radical form, our answers will always look the same if they are actually the same. If I stay at the square root of 80 and you get 4 times the square root of 10, those don't look the same. So we're not going to know if we have the same answer. Okay, but if I break this down and change it into simplest radical form, and yours is in simplest radical form, they will look the same if they're equal. So simplest radical form, it's just a way to take some numbers out of the radical. So if I rewrite 80 into its prime factorization, so if I break it down into just all the prime numbers that you multiply together to get 80, so 80 is 8 times 10. 8 is 4 times 2. 10 is 2 times 5. 4 is 2 times 2. So the prime factorization of 80 would be 2 times 2 times 2 times 2. Okay, 1, 2, 3, 4 2's and a 5. Okay, I'm not going to use any of these numbers again because they're broken down. Okay, the 10 is gone. It became the 2 and the 5. The 8 became the 2, the 2, and the 2. So really, I've got the square root of these numbers all multiplied together. Now, if you think about what square roots do, square roots are the opposite of a squared term. So if I have the square root of 5 squared, well, 5 squared is 25. Square root of 25 is 5. So square roots cancel squareds. So if I can get some numbers squared in here, those squared numbers are going to cancel the square root above them. So I've got a pair of 2's, which I could rewrite as a 2 squared. Here's another set of 2's that can be 2 squared, and then I've got a 5. So this squared will cancel the square root above it and just leave a 2. This squared will cancel the square root above it and leave a 2. This 5 cannot cancel the square root that's above it. So the simplest radical form turns out to be 4 square root of 5. Okay, now that example I had said if you had 4 square root of 10 and I had square root of 80, we wouldn't know if they're the same. Now we would, because I have 4 square root of 5, which is not the same as 4 square root of 10. Okay, so now we would know we don't have the same answers. Before, we wouldn't know for sure, but now we would know for sure. If we both had 4 square root of 5, we would know that we have the same answer. And by breaking it into simplest radical form, it guarantees we're going to have the same answers. Okay, so all this is going to be used in our segment addition problem. So remember, I'm trying to determine if B is in between A and C. So I need to find out if AB plus BC equals AC. So what's the distance, or what's the length of AB? So we can use distance formula if you want, or you can use what would look like your right triangle. Okay? So for AB, okay, how far over am I moving? What's the difference in my x's here? Okay, they're 2 apart. So this side of my triangle would be 2. The height of my triangle is 3 apart. So I'd have this. So to find AB, I would do 2 squared plus 3 squared. And that should equal this squared. Okay, that should be c squared. So if I square root this, so now I start solving this. 2 squared is 4. 3 squared is 9. So I get the square root of 13. Okay, and that's not going to break down because 13 is prime, so I'm just going to leave it as the square root of 13. I'm not going to do decimals. Okay, we don't want decimals because then we're rounding. If we round and start adding rounded numbers together, they're not necessarily going to be the exact same as what I want this to equal. So I want to keep it exact. This is an exact number. I'm not rounding it at all. So next I need to look at BC. Difference between my x values and BC is 6. To get from -1 to 5, that's 6. So I have 6 squared. The difference in these is 9, so I have 9 squared. So I've got 36 plus 81. 36 plus 81 is 117. And let's see if that breaks down. So I know that this one is divisible by 3. And the trick I'm using to know that is you add the numbers together. 7 plus 1 plus 1 is 9. You can divide 9 by 3, so you can divide 117 by 3. So 3 goes to an 11 3 times, drops a 2, 27, and 3 goes into 27 9 times. 39 turns into 3 times 13. So I've got 3 and 3, so that'd be my 3 squared times 13. That squared is going to cancel above the 3 and not above the 13. Finally, I need to do AC. So the difference from A to C in the x value would be 8. -3 up to 5. So -3, -2, -1, 0, 1, 2, 3, 4, 5. That's 8 spots. So 8 squared. To get from 15 to 3, that's a difference of 12. So 64 plus 1, 44, which would be 208. Let's break this down. I can put 4. 4 goes in there. 52 times. 52 is divisible by 3. Or not. Nope, it's not, because 5 plus 2 is 7. But 2 goes in there. Okay, anytime you have an even number, you can always do 2. So this is going to give me 26. 26 is 2 times 13. 4 is 2 and 2. So I've got 2 squared. I've got another 2 squared, and I've got a 13. These 2's are going to cancel the square roots above them. So really this is 4 squared of 13. So now we got the square root of 13 plus 3 square roots of 13. Does that equal 4 square roots of 13? It does. Okay, this is 1 square root of 13. This is 3 square roots of 13. So I have a total of 4 square roots of 13. So I've got a true statement here, which means yes, B is between A and C, which also means A, B, and C are collinear. So there is some line that contains all 3 of these points. Okay, so kind of a lot, because we had to review a couple things. We had to review distance formula and simplest radical form. Anytime you're getting a radical from here on out, we always want to use simplest radical form. We're not going to use decimals. And segment addition postulate. So this is going to be a big problem. This is definitely something you're going to see on the test. I'm going to give you 3 points and say, determine if B is between A and C. And you're going to have to make sure that these add up to equal AC. If I had gotten something else here, so if I had, square root of 5 plus 3 square root of 13, excuse me, does that equal 4 square root of 13? Well, no, it doesn't, right? Because the only way I get 4 square root of 13 is with another 1 square root of 13. So this would be no, and then I would know that they're not collinear.